last time that we have now introduced basically quantum field theory and the lattice regularization, always in the framework of functional integral formalism in Euclidean space. But so far we have been limited to scalar fields or multi-component scalar fields, but what we still have to do is to introduce state fields and fermions. But this can be done rather quickly, so then we will come to complete formulation of lattice QCD and see some results and what is the status nowadays in the 21st century. So first of all, a reminder about gauge interactions in the continuum. Just go to this because when we will do analogously afterwards everything on the lattice already. So we had before usually neutral scalar fields, which were real functions of space-time. Now we have a complex or charged one. So a typical Lagrangian would be of this form. So we see that it is
we have the fraction half. Charged scalar field doesn't have half.
Aha, well, it's a matter of normalization, but yeah, you could skip it. Well, because you have the real and the imaginary part. Well, I would consider, if you consider these two components of a real scalar field, then I would put the one half. But in any case, I mean, you can restate the field and okay, then you change also the potential. It's a matter of convention anyhow. But I would usually even there write the one half. But it's okay, by restating the field you can essentially avoid this. But if you consider it as two, okay, if you decompose it like phi star, phi is a phi 1 plus I times phi 2, then you have here essentially 1 half delta 1 plus delta mu phi 2. So this corresponds to two scalar fields, which are if the potential makes them keeps them independent, which do not mix. So we have two real scalar fields, and the 1/2 is in this case would be natural. But again, it's a matter of convention. It's not really physics. So at this stage, we certainly have a global symmetry. Global means, first of all, a symmetry means that we can perform a group of transformations, a group in the mathematical sense of transformations which leave the Lagrangian and therefore at least the action invariant. There are some cases where maybe only the action, the integrated version is invariant, but here we certainly have this property of the Lagrangian as an invariant. And so a global symmetry means that we perform the same transformation all over space and time that we consider. So it is basically one transformation of the field independent of the component x. So here we can obviously perform a U1 rotation given here. Okay, at this stage this could be written with one coefficient in the exponent, but I decompose it for later convenience, where g phi would be the angle, let's say, running from minus pi to pi, and g is then a factor amplifying this angle, so a scale factor for the phase. So they are both real, and if we perform this transformation, obviously nothing changes here. But this is only one transformation parameter all over space-time. This is not very much. Usually we want to optimize symmetry because this constrains the results a lot. And if we want to promote this to a local symmetry, then they are much more ambitious. So that will mean now phi can be a function of space and time as well. So in each space-time point we can do such an independent rotation. If we achieve this, then we have a lot more symmetry. If we need that or not can be argued, but it turns out to be a very successful concept to describe particle physics to construct such local symmetries. And in this case, we see that the potential is invariant already, but the kinetic term here is not. because okay, if this is dependent on x, then obviously the derivatives can also act on the phase here, and then this term changes. So if we want the modified version of the Lagrangian to be locally invariant, we have to do some manipulation in these kinetic terms. And this is well known that we replace the derivative by a covariant derivative. The derivative has an extra term here, which comes again the same coupling constant g now, and an extra field here. And if we perform this transformation of phi to phi prime, then this extra field of a vector character transforms as well, with such an extra term, which is the derivative of this phase that we attach to phi. And it can easily be shown that this is now locally symmetric. So we look at the covariant derivative transformed, applied to the field transformed. So this is the covariant derivative after the transformation with the a prime already inserted, and this is the phi prime, so phi with the local phase factor. Now if we apply this, first we drag this exponential factor to the left. The derivative can act either on the field phi or on the phase, so with these two terms, and then we have this term where a prime is already inserted from here, and then there must be a cancellation. This is not a surprise, the construction is done such that this term and this term cancel exactly. Then we are left with this term, and this is exactly the covariant derivative without transformation of the field, without transformation with this extra factor. So if we look at the whole kinetic term here, we have then two extra factors, the first one with a star, and then these phase factors cancel. So the whole kinetic term here is invariant as well. So with this addition, we have achieved local symmetry or gauge symmetry. I consider this synonymous. Literature often writes local gauge invariance, but actually to me it doesn't make sense. Gauge invariance is a local symmetry. So this is what we have implemented in this term. Now we have introduced a new field of a vector character, a gauge field, and actually also this field of course can represent physical particles. But to do so properly, it should also have a kind of a kinetic term. And so let us construct a term which only depends on the mu, which we can act then. And of course, it must be gauge invariant. It must be invariant under the transformation that we have just shown. Otherwise, we would destroy the nice property again. A building block which has this invariance is the field strength tensor given here. So this is the transformation of a field strength tensor. Now if we apply, if we insert here the A primes, then we have these extra terms, and in the usual flat space then these derivatives commute, so these terms cancel. So this is the same. So this is a building block for a kinetic term, but of course we want it to be scalar, so we build an FMU combination here. Okay, we have a double sum here, so we divide by 2 and another 2 for the usual kinetic term, so that's why 1/4. And in Minkowski space it would be a minus, but in the Euclidean space this is a plus here. So this is the well-known kinetic term of the gauge field, of the abelian gauge field, which is indeed massless, and of course we would not be allowed to write, say, a mass term here, because this is obviously not gauge invariant anymore, so the gauge field, as we inserted in the Lagrangian, cannot have a mass term. Fine. Now we have already the construction of a gauge invariant Lagrangian of scalar vector dynamics. This is not completely hypothetical. Such a complex scalar field could, for instance, describe Kuko pairs in a superconductor. So it consists of 2 electrons of opposite spins, and if you look at it from a distance, not of a very high energy resolution, it seems like a spinless complex particle. So this is actually quite a realistic description of a Kuko pair. Also in a superfluid, you have similar effects. So then we have this term here that we constructed, the potential, which is trivial gauge invariant if it depends only on phi absolute square, and then this kinetic term here, and the partition function would be given in this way. Now there are some remarks of caution. First I write here a functional integral of all phi scalar configurations. That is fine. But then I write here symbolically also the same over all gauge configurations, and here the problem begins, because we know that if we perform, we have a lot of configurations which are actually invariant, equivalent, because they are related by gauge transformations. So they are not really the same, not really different, they are physically the same. So this functional integral should only capture the configurations which are really different, and that is not easy to achieve. So there are tricks to put an extra term here which fixes the norm, which avoids these extra copies. However, yeah, this is known in the literature as for the Popov term. It's a kind of a Lagrange multiplier field which is added here. And then, because this is also a field, it introduces kind of particles which are not really physical, so they are known as ghost particles, but they are still complicated to deal with. And another problem is that even this term does not fix the gauge completely, because it can still perform large transformations to escape from that and have then still some copies known as Gribov copies. This is an endless subject. This is very tedious to do this properly in the continuum, but on the lattice we can essentially avoid all these problems. So now we don't look at this in detail. I think Sorella is a great expert on this, in Rio. But here we basically ignore all that and we proceed to the different construction which is directly on the lattice, where we do not need the gauge fixing.
Excuse me, Wolfgang, will you explain this additionally, that lattice avoids the problem of gauge fixing?
Yes, in some sense. Not in, yeah, at least the general idea. Yeah, I will.
Okay.
Yeah, yes.
Okay.
I will come now to the lattice construction and see that. Okay, there we deal with a construction which is gauge invariant to start with, and why this fixing is not needed. Yeah, this we will see. Basically, the idea is that we don't deal with these fields in the algebra, but we deal with fields which are directly in the gauge group, and then the equivalence, this kind of captures all the equivalent copies. So but that is something that in the continuum is not really doable. But okay, I will continue to that just now. So if it's not clear, then please repeat it. So now let's come to the lattice. So let's say we have again the same scalar action on some discrete sites now, which I call x, y, etc., with a space in A. Then the initial scalar action without gauge fields can be written in this schematic form. This is a sum over all the double sum of all the sites, and there's a coupling here which I can write as a matrix. For instance, in the free case, okay, we would have this discrete second derivative or discrete Laplacian if we sum over the mu, and then again a diagonal mass term. And if we have, we can also have multiple components here, so then we would have another delta ij here, should be here as well. Sorry, I forgot that. And so this is now in C to the n. It's a bit more general than before. Can be an n-component complex field. This is the Hermitian conjugate. And we have, first of all, on the lattice, on the regularized level, directly the same symmetry as before, generalized to n components. So it's a global UN symmetry. If we apply a UN symmetry transformation to the field, and in some site, and the same one in any other site, then this commutes with the n, because because this is space independent, and then this G and G dagger cancel, and then we have this global symmetry. So now the challenge is to promote this to a local symmetry, and to do so directly on the regularized level. And so then we are sure that we have controlled gauge invariant system under regularization, and if we take the continuum limit, we are sure that we keep gauge invariance. It's very dangerous to break it on the regularized level, because then it's unlikely that it will come back in some limit later. So to promote it, first of all, we have this this term here. If we now want to make these factors g local, so g of x and g of y here, if this is an off-diagonal term, then this does not naturally cancel. So here we have an extra term that has to be cancelled by some modifications of the kinetic term that we saw before. And in particular, so if we look at this is already invariant, this is already invariant, but what we have to deal with are these shifted Kronecker symbols here, which couple to nearest neighbor sites. So these Kronecker symbols have to be modified such that we have this invariance. And we see that actually it's obvious what to do, because here we have a product of two elements in the group is again in the group, and we replace now this shifted Kronecker symbol by a link variable which we put on the link here, not on a lattice side, which connects x to x plus a mu. And on this link here we put a variable which is again in the gauge group, and which transforms on the gauge transformation such in this way, so that we multiply from the left with a g and with the right with a g dagger, both here at the starting point, at the end point. And now if we consider the transformation together with the phi's, then we have this dagger here. Dagger transformation cancels against this one, this transformation cancels comes from here, cancels against that one, and so since this is unitary, they cancel exactly. Or in general, we have to take the inverse element. So we have here, first of all, we have implemented gauge invariance on the regularized level. Now, I have to discuss a bit what this actually means. And so far we have only constructed this on the regularized level, but of course we want to see the relation to the continuum field. So this should be still worked out. So first we can say this would be our continuum field, and if we simply integrate over the path from one lattice side to the nearest neighbor, so if we integrate over this path here, then we have here a new variable, link variable, which we call ax mu, which also lives in the link, and its exponential up to this constants here is then what we identify with this element in the gauge group. Now, if we perform a gauge transformation as we introduced it before in the continuum, so this would be of this form, and now this affects in this integral the boundaries only. So we have then gx is of that form, and then we have gx, and here the minus the inverse one at the end point. So this makes these two boundary terms of this integral are manifest in this exponential form. And now if we plug it in and compare it, it is exactly what we had before. So we confirm that this connection here with the this transformation that we anticipated corresponds exactly to the continuum transformation with this identification. So what we did is in fact related to the continuum formulation, and we saw that this is gauge invariant. So we have a discrete covariant derivative. So it proceeds in a finite step over a link, but it is fully covariant. So we have now implemented the most important symmetry, namely the gauge symmetry, which must be exact for the theory to be a consistent gauge theory. And the difference from a continuum formulation is that we don't treat with fields in the algebra, but with fields in the group. So this is known as compact link variables. So this is, first of all, it is convenient for simulations if we want to construct configurations. We only have to explore a finite, compact space of parameters where this is located, whereas this one is non-compact, so this runs to infinity, so it's much more practical to deal with. And in this form, so if we deal directly with the A nu, we see that the A nu actually captures a whole of equivalence copies of the A, right? If we shift this by 2 pi, 2 pi divided by JA and so on, so we get the same again. So if we deal directly with this variable, we capture automatically the gauge transformed copies of it. So this A nu is a gauge invariant quantity, and if we integrate over this, for instance, with the R measure of a compact group, then we are not doing an overcounting. Then we are counting exactly the physical degrees of freedom. So this is something that in the continuum it would not be feasible to use the A nu. Then there's in the continuum there's no alternative to the U nu. There's no alternative to the elements in the algebra, and then we have all these problems with the extra copy and the gauge fixing. So
I'm afraid that I did not get your point precisely.
Okay.
You say that when you use the U's,
Yes.
you sum over different configurations of U's,
Yeah.
you are automatically summing only the physical degrees of freedom.
Yes. Yeah, you see, because
I did not get this point.
If you fix such an A, if you say, okay, this is my U which is fixed. If you translate it into A nu, this is not unique. There can be many A nus which lead to the same U.
Yeah.
And so we actually capture a lot of gauge copies which are equivalent. So these are the equivalent copies. So if we integrate, let's say we parameterize the U, let's say for SUN with a H measure, this is a compact space, then we do not have extra copies that distort the relation. So the functional integral gives us the correct answer without destroying this good.
Let me see if I understand.
Yeah.
You say that this U mu is in fact a gauge invariant object. If you change A mu for a gauge transformation, you get the same.
No, actually, okay. No, yeah, you're right. At this point, no, I should not say the U mu. Yeah, you're right. The U mu is in fact not gauge invariant.
It's not gauge invariant.
It's not gauge invariant. But okay. But so okay. Yeah. No, you're right. The U mu still has to be U is a building block to construct the action in a gauge invariant form. This is what we will do next. So if we put several mu u's together to build a closed loop, a Wilson loop, then we have a gauge invariant form. Yeah, I should have postponed this comment. Yeah, and once we have that, so then we will have full invariance under the gauge transformations in the A nu. Yeah, you're right. The U itself can actually change with the gauge. Yeah, this is if you do a gauge transformation here. Okay, yeah, we see that. Okay, actually we see here that it can change with the gauge. But if we still have to construct. So far, this is not the action. This is only a building block of the action. We still have to build the action also for the pure gauge term, and then I can say we have something which is fully gauge invariant on the regularized.
Let me ask you in advance.
Yeah.
The problem with the continuum formulation is that you have a gauge invariant action. So if you sum of overall gauge configurations, you pass through many values of the action which are the same because they correspond to simply to different gauge transformations. If you put in the lattice gauge invariant action, why don't you have the same problem? Because if you pass through several configurations U which differ one from each other from a gauge transformation, they will furnish again the same action. This is the point I don't understand, in fact. But if you want to postpone the discussion, no problem.
Let's maybe look at the construction of the pure gauge action in terms of this view. But the question is actually tricky, but the difference is of course that these UVs are compact, so they do not run away to infinity. So you can sum over a set of configurations. If you do this with a finite set, they come with the right statistical weights, and they correspond to, they give the right contributions to an expectation value.
You can limit your sum to some predefined set, and so you don't have to.
The set is not predefined. The set is actually infinite. But what we always do, also in the previous cases, that we generate configurations, a finite set of configurations by Monte Carlo, which has the probability distribution given by the action of the system. And if we use this gauge invariant action, then this statistical weights are correctly distributed. So if we generate 100,000 configurations with these weights and sum over them to compute the expectation value of an endpoint function, then the answer is correct up to statistical error because the set is incomplete.
You say the problem is solved at the level of the Monte Carlo sum. The Monte Carlo method.
Yes, there is no gauge ambiguity does not affect the expectation value calculated from a set of configurations which is generated with the action given in this form. So of course you have the set is theoretically infinite, and to have the exact result you will need an infinite number of configurations, which is not so good, but then you can compute, you measure this some thousand times and you have an error of a few percent, and up to this uncertainty you have the right result, but the gauge ambiguity does not distort this result in any sense. Yeah. So in this sense, yes. Yeah. So you're right. And this here is still gauge variant, but then the overaction not. But then once we can explore this space without in a compact parameter set, and if we take out points there, even with the probability of the gauge action, then you're doing statistically the right thing, and the only limitation is the precision.
The point should be that you are not performing the complete sum, but through Monte Carlo you are choosing some specific configurations which are representative from your set. And
this is nothing new. This is the same.
The errors you make in this procedure are compensated somehow, and no problem at the end.
Well, the errors are there to stay. You have to live with an uncertainty. So they shrink with the inverse square root of the sample that you have. If you have 100 times more configuration, it will be 10 times smaller, and you will never get it down to 0. But maybe to 5%, and if you do a lot more work to 1%, you will never get it to 0. But this you have to live with. On the other hand, it is fully non-perturbative, so you can work at a finite, even a strong coupling, and you do not have an error because of the unknown extra terms in a perturbative expansion that you truncate. So in this sense, just say, this is the same problem with the uncertainty you have also without gauge fields, that if we deal with the method that we showed before. But in any case, gauge fields do in this regard not introduce an additional problem in this formulation.
Let me see if I understood. This would work if you were able to prove with a case that you could exactly calculate it, so to compare with the simulation.
Yes, in the
technique, the way to do this.
Yeah, as you know, there are there are few cases of field theories which you can compute exactly. Yeah? Some of them exist.
So if you prove the technique works for this case, so you'll be confident that the technique is good.
Yeah, in these cases it works. Yeah? And if you if you deal with perturbation theory and then perform simulations at a very weak coupling, then you see that asymptotically the results also agree. Now if you go to stronger coupling, then you have nothing to compare with anymore in the continuum. So then the continuum, but what you can still compare with is of course if you deal with QCD, phenomenological data, pattern masses, and if this also works, then we think we are on safe grounds that we have the right formulation. But now there, okay, that's the problem. We have nothing in the continuum anymore to compare with the theoretical aspect. So in some sense this defines, if you take this procedure of final and final lattice spacing, this defines the field theory on the non-perturbative level. Okay, let me now look at this, at the gauge action, the Q gauge action. So what we do is now we take a blockade. A blockade is simply the minimal square. It can be, this is a plane out of can be a four-dimensional space, so we take a plane out of it and the minimal square here, so and we multiply this times this times this times this, so we follow a path here, a closed path. This is an example for a Wilson loop, and we call this now the blockade variable. Since it is built of link variables, it is again an element of the group. Here U1 in general could be any Lie group. And since the initial point and the end point are the same, this object here is now fully gauge invariant. Since, okay, this is also true in the continuum. If you build a closed loop and integrate along this loop the gauge fields, then you have a gauge invariant quantity because the transformation affects the initial and the end point, and if they are the same, it compensates. So this is the simplest non-trivial ingredient that we can construct. And so we have identified mu with such a compact, with a non-compact link variable in the exponent. Now this blockade variable is given, okay, I call this f mu x. To justify this term, let us decompose this into the four contributions that we have from the links here in terms of the A mu. And if I rewrite it in the form, we have then this link minus that link plus this link minus that link. This is exactly like discrete derivatives of delta mu A mu minus delta mu A mu. And this is still divided by A. So this is exactly a discrete version of a field strength tensor. So that's why it's a reasonable notation to call this F. And then we say, okay, we can also identify this with the exponential of a discrete field strength tensor. So this is, in principle, this is not necessary if you want something gauge invariant, but of course it is nice to see the relation to the continuum formulation. Now, this is still not the action, but this is what we use to build the action. Now we take, say, this linear combination with a prefactor and sum over this. Now, if we have this u, okay, this is an exponential here. First of all, the 2 cancels if you expand in, let's say, if you expand in a small g or a small a square, it's equivalent here. Then, let's say, close to the continuum. First of all, the 2 cancels. Then the linear term cancels because this is a u and a u star. And the next term, the first one which survives, is then an f mu f mu. And this is, and the prefactor here also makes exactly this 1/4. So this is exactly the continuum limit, you get exactly the continuum formulation. Here you would have some higher terms if you carry on the expansion, but they come with higher powers of a. So you can say in the continuum limit, you get indeed the familiar term from the continuum formulation. So this is a valid lattice formulation, the regularized formulation of the continuum action, and since these variables are now really fully gauge invariant, since it is only built on these blockade variables, So this is gauge invariant to start with. Right? If you have, for instance, if you just truncate the momentum, for instance, you will not get this property. So so in this sense, we do not need to put an extra term here for the Popov kind. You can do this. It doesn't do any harm because okay, it is allowed to still fix the gauge, and some people do that for practical purposes because the simulation is then maybe a bit less noisy and so on. For instance, Teresa Mendes is always doing that, but theoretically it is not necessary if you say I integrate, I have a function integral over these u variables, I use this and this term as my action, it gives the right statistical weights, and if I do a measurement, numerical measurement with it, the gauge copies do not distort it in any sense. So in this sense, okay, in this sense, this is a clean formulation. Now, this is all for the example of the abelian gauge group, which is the simplest case. Non-abelian gauge groups, it is basically the same, but it is not completely straightforward. It is okay. The result looks like a straightforward generalization, but it takes a few pages to demonstrate that, which I will not do here. I can refer to the literature if somebody is interested. What one does is one introduces again link variables which are in the gauge group, for instance in SU3. One introduces the plaquette variables again around such a plaquette, which consists of the product of 4 link variables, so it is again in the gauge group. And now what you see at the star is then replaced by a dagger, of course. And then if we have several components, you have to take a trace here. And for the case of unit link variables, then also the plaquettes are unity, then the normalization factor here, so that this should be 0, and this is a 6 instead of the 2, because of this trace, and all the rest is actually what one can guess as a generalization. To show that this is correct, again, it is not completely obvious here. This takes a few pages of calculation, but yeah, Wilson has done this around in the late 70s and convinced people that this is correct. You get again in the continuum limit the right formulation plus extra terms which are suppressed in higher orders of A. So if you make A smaller, then you converge to the right to the continuum result. So, okay, this is about gauge fields. Now the next problem is fermions. Okay, this is very quick. Of course, you are familiar with fermions. So the first historic attempt was to write the Schrödinger equation in a relativistic form. This is actually what Schrödinger had in mind himself, and then he noticed that this doesn't work well for the hydrogen atom. So then he took the non-relativistic formulation, and for some reason it worked much better. If we interpret here the derivatives as operators, then we would have here this energy dispersion relation of the Klein-Gordon equation. And one problem that puzzled people was that this seems to have a negative energy solution. This is then avoided by the Schrödinger equation. And this is what motivated Dirac to say, well, if this is generic for quadratic equations, so we try to linearize this. So this is his linearization ansatz. Say, okay, I have now a linear derivative and some coefficient here. And if we square it, of course, we have to get again this Klein-Gordon operator. So we have to go back to this formulation. And we see that with bare numbers, gamma mu, this does not work, so we have to require this anti-commutativity property. This is an anti-commutator. If we require this, then it works, and this in 4 dimensions requires at least 4 times 4 matrices. 2 dimensions you could get along with the Pauli matrices, but in 4 dimensions you need at least 4 times 4. And then also the psi that you act on must have these 4 components. So this is a spinor, and this is just enough to capture particles and antiparticles. This is what inspired Dirac to predict the positron. The fermion was for him only the electron at this time, to predict the positron, which was then found a little bit later. And he also noticed that this works very well for the hydrogen atom. But actually, I should say that the initial problem with the negative energy is not, it's not obvious that this solves the problem. So if we deal with relativistic quantum mechanics, it is actually still have this negative energy solutions, but if you go to the field theoretic formulation and you define energy by an exponential decay, as we saw before, then the negative energy solutions are really resolved. This is Pesky and Schroeder discussed this in detail. This is not at all obvious why this why the negative energies really disappear in this formulation. Now, okay, we want to do quantum field theory, and the only reason why we need Schrödinger's equation is to have the building block here and to build the action. So we introduce now fields. And in the Euclidean space, I introduce psi and psi bar as independent fields. So we put, okay, this is of course, there's a transformation between them with gamma 0 or gamma 4, but if you consider them as real, then you can see in the Euclidean space this works as a separation. And now I write the partition function over a giant matrix, matrix here M. So we have psi, these indices run over all positions, space-time points, or lattice sites, and in each lattice sites over the 4 spinor indices, and in each spinor index over possible additional degrees of freedom, flavor, color, and so on. So they run over all fermionic degrees of freedom. So this is usually a huge vector, and this is then the column vector, and the M is then a huge matrix capturing them. So all theories of interest are of this bilinear form. If you write higher terms like a psi to the 4 term, there are theories like that, like the cross-model model or non-Euler-Rossini model, but we can, with a little auxiliary field, we can integrate it out and bring it back to this form. So this is the form to deal with, and this is the very general ansatz. And of course, the Dirac operator must be encoded in this matrix M somehow. This derivative, of course, captures somehow neighbors, and we can turn it into covariant derivatives as we have seen, but how to do this exactly is actually a non-trivial question. But this I suspend to the last lecture. This is quite a tricky issue, how to formulate the lattice Dirac operator. For the moment, I suppose that this has been done somehow, and later we will show that it can be done in some reasonable way. So again, we can include here possible gauge fields, which then would then be also integrated here. And now we have to do justice to the Pauli principle. In the canonical formulation, this is done by operators which do anti-commute. Here, the whole idea of functional integral was to get rid of this operator from the beginning. We only have field variables, so to still do justice to that, we need field variables that anti-commute themselves, and this is done by Grassmann variables. These were introduced sometime in the 19th century by a mathematician named Grassmann, but only 100 years later they were then discovered as the right quantities to describe fermionic fields in quantum field theory, in the functional integral formulation. So if we introduce some variables, eta 1, eta 2, eta 3 and so on, they all anti-commute with each other and also with themselves. So that's so it looks a bit like Dirac algebra, but it is important to notice this difference that also the square of a Grassmann variable itself is 0. So this is different from the gamma matrices. So if we write a function of a simple Grassmann variable, all we can do is write, let's say a Taylor expansion would stop at a linear term because we cannot construct anything more than that, where A, B, let's say, would then be complex variables. And then we have to introduce but still, I mean, life is getting interesting if we have a lot of these variables, then there are still non-trivial effects. And then we have to introduce also derivatives and integrals, and the derivative is what you would expect. So it's, if you derive the number itself, you get 1, if you derive another number, it's 0, so that's the usual thing. But if we do an integral, first of all, an integral does not have boundaries. There's just either you do the integral or you don't. There's no notion of a boundary. And then if you require this integral to be in translation invariant, so invariant under this is a j plus a eta k. Then if you do such a translation and you require this to be invariant, you have to require that the integral over this is 0 if you integrate over a different variable, and this is only achieved with this rule. And then you can say the integration over the variable itself, the d eta j, okay, this gives a contribution, a final contribution, and by convention we normalize this to 1. So strange enough, the integral has now the same effect as a derivative. This looks a bit funny. So it's not like if you integrate, you put this to a to j, eta j square, which will be 0, that will be the other, that will be the wrong answer. So this was recognized as the proper definition of the integral. And now if we integrate all these variables here, we get then the functional, the Grassmannian functional integral. So let us look at a completely trivial, unphysical case of only one component field. So we have here psi bar and psi, so two Grassmann variables, and we have this exponential, and m is just a number in this case, no? Because it's only one component. Now we do first the expansion of this exponential, so this is 1 minus this plus higher things. The higher orders have at least 4 powers of the Grassmann variables, but only 2 variables are different, so then there must be 0, right? Because we necessarily square the same number, so all the rest must be 0. Then if you perform the integrals, this here gives also 0, because you integrate over something which is not in the integrand, so this is also 0, so only this term can give a contribution. The m, this is a real or complex number, we can take this in front of the integral, and here I still exchange the order, so let's say I put psi to the left hand side, so this cancels the minus here, and then you have the integral, the psi gives 1 and psi bar psi gives 1, and so we are left with exactly with the number n. So this is here we can carry out the integral completely. Now, of course, we want to see what happens if we have many variables. So if we have a lattice of 32 to the 3 times 64, and in each point 12 components, so we have typically millions of components, which we cannot compute explicitly, but the case of 2 components we can do, and then we can guess how it goes on. So we have 2 components now, so that means 4 independent variables or field, Grassmann field components, psi bar 1, 2 and psi 1, 2, and then the integral, the partition function would be of this form. Again, I expand the exponential here, 1 minus this plus this minus, here we have at least 6 factors. With 4 components we necessarily square something, then all the rest must be 0. Right? And here we integrate 4 times, but we need 4 integrals for different variables here, so these 2 terms cannot contribute either because of the integral, so we are left with this term only. We take the 1/2 in front, and now I write this term in full here. Just write this, this is the 2 times 2 matrix M, write this in full here and take the square, and we see that we have now to take the terms under the square which only have different factors. So this term, for instance, can be multiplied with that one, that gives a contribution. But you cannot multiply it with this one, we have a 0 here, or here we have a 0, so then we have this psi bar 1, psi 1, psi bar 2, psi 2, and this n1 and 2 and 2 and 2 and 2. And then the other combination is multiplying these 2 terms. We always have the same twice, because this is the packages of 2 can be commuted. So this gives in both cases a factor of 2. This cancels the 1/2. And here we have the inverse order. To arrange for this order, we have to move this twice and this once. So this gives 3 changes of the sign, and we have a minus here. So we have here minus n1, n2, n2, n1. And now if we do all the integrals here, we get again, okay, we have to move maybe this to the left, then we have a minus 1 to the 3, minus 1 to the 2, minus 1, so it's a minus 1 to the 6, this is all 1, and we are left with this term here, which is the determinant of m, and now we can guess how it goes on. This is a general rule, it can be shown by induction and so on, that for any number of components we always end up with the determinant if we have this functional integral. And unlike, let's say, real variables, we don't even need, okay, for real variables we need to avoid negative eigenvalues here because it's divergent, but Grassmann integrals are always convergent, so we don't even have to require anything about the spectrum of m, we always get this determinant of m because this series always stops, this is always truncated at the suitable order. So this is the completely generic result. Demonstrating this would again take a few more pages, but which I will not do. So this is, it's actually one of the exercises, it takes a couple of pages. So this is the completely generic result. So if we have such a linear exponential, we perform the functional integral, we have here then the determinant of this m. And of course, if you have gauge fields involved, then they will be included, the link variables will be included in this m, and this determinant also depends then on the gauge configuration. So for the moment we only integrate out the Grassmann fermion fields, and then we still have to handle this as the integral over the gauge fields, which include this, and the pure gauge term, which is not written here. So to start with, one would probably think that we have to teach the computer to deal with Grassmann variables, which could probably be done, and maybe somebody has done it in the world, but in this context at least we don't need it at all. So we only need to compute determinants, or to know these determinants in some way. But this only is a bit ironic because, okay, typically we have here millions of components, and calculating this determinant has to be done very frequently in the simulation. Every update has to know the action of the new configuration. So this is what slows down the simulation. This is the bottleneck. All the rest of the simulation is quite fast, but this is actually the limiting factor to deal with. And of course, now people have thought about over 30 years about advanced techniques, how to do this optimally fast. It is still the limiting factor, but just to mention this without details, the optimal algorithm circumvents the computation of the direct computation of the determinant in the following way. One introduces a set of it's called pseudo-fermion fields. Actually, there are multi-component scalar fields. They are auxiliary of a Grassmannian type, but we can write in this form we get an inverse determinant. So we can write this determinant here as e to the phi minus 1 here, and then update these gauge fields. And then what we still have to do is to compute the inverse of the matrix, which is also unpleasant if you have millions of components, but it is not as bad as calculating the determinant. So these matrices are sparse, so they are localized. Most components, most entries are next to the diagonal, and then there are efficient tricks to compute this inverse. And this is bad, but not as bad as calculating the determinant. So if we deal symbolically with this extra gauge fields, which all disappear in the final results, then we avoid the direct computation of the determinant. So this is what the so-called hybrid Monte Carlo algorithm does to make it as fast as possible.
Wolfgang,
Yes.
how do you compute fermion Green's functions, multi-fermion Green's functions?
See, you have, this is now the partition function. Now if you want to have Green's function or endpoint functions, you take an expectation value like this. Okay, you have then this e psi, and here some fields. Okay, let's say x, psi, y, and so on, and then 3 to the minus s. Yeah. and that is 1 over C. Now, okay, if you if you evaluate this, you can also already this converts, or this is also converted into an mx minus 1. So and if you have several fields, then you have this block decomposition in pairs of 2 according to Wick, right? A Wick contraction. So everything that you want to compute goes back to this matrix M at the end. So okay, I'm not saying that this is easy, but at no point you have to deal explicitly with the Grassmann variables. The computer does not need to know it. You just have to. And this is also a homework, by the way, to calculate this for free field to show that this expectation value, x, that this corresponds to this inverse method. Sorry, this is no, I should write this -1 and here x1. Yeah. So it is actually similar to the scalar case, but okay, we have just an inverse power. I mean, the only difference is that in the scalar case this would be 1 over determinant and here this determinant. So amazingly it looks completely different from the beginning, but then it turns out to be the result turns out to be quite similar. So if everything is encoded in this M here, and its elements and the elements of its inverse and its powers and so on. Yeah. So it's not easy, but conceptually it is actually straightforward to do this. Now, if we want to formulate the full QCD simulations, QCD formulation, QCD known as the gauge theory, which captures the strong interaction. So we have then quark fields, in principle 6, but if we are not interested in some exotic high energy situation like LHC or the early universe, then we are usually happy with 2 and maybe some percent correction of the third, the strange flavor. This is what really contributes to our daily life, and they are interacting to the gluons, which are this SU3 gauge bosons. So in this case, we would have here a long array of psi bars and psi. For each flavor, we have then this. For each component, we have these 4 spinor components. Then we have 6 copies or 2 plus 1 copies for the flavors. And for each element of them, we have then still 3 copies to have this SU3. So I just write this, and then we have here then we have a 3 times 3 block inside this M, which is huge, of course. And first of all, we would have a global symmetry, which is actually U3, but we know that we only promote SU3, the subgroup, to a local one. So then we can multiply this with a U dagger and a U here, and then so we get then the local UX symmetry in SU3 if we apply the procedure shown before to these blocks of 3 components which capture the 3 colors of a specific quark flavor component. Now the covariant derivative in this case is given here as the derivative plus this is what before worked is just as the coupling times a phase. Now, of course, this phase is generalized to a sum over the generators, in this case 8 generators, that can be written, for instance, by the Gell-Mann matrices here. Okay, there should be Hermitian in any case and traceless to as SU3, and then there are different representations. And if you build the sum here and each coefficient in the sum is actually a field, then we have altogether this gauge field, which I write with the shorthand G mu M, G mu of x. And I changed the notation a little bit compared to before. Case before I include also the gauge coupling, the GS, G strong into this field. So the whole covariant derivative is now a d mu plus this G mu. And the gauge action is actually, okay, we should now build only terms based on covariant derivatives, not of simple derivatives. Then we have something, then we have a chance to get something gauge invariant. And if we build the commutator of this, then we have this, term. And this is what we call the G mu, the field strength tensor. And we see that in addition, in the abelian case, we do not have this term. So now, but since the gauge group is non-abelian, we get this extra term. And the gauge group is then this again the field strength tensor G mu with a trace now. And this prefactor we have to, since it is included here, we have to divide it off at the end. So this is first of all the gauge action in the continuum. We can do exactly the same on the lattice with this in the SU3 gauge group. And this term here has the consequence that the gluons also interact among each other. So we see from here that there can be a line of, there can be terms with two G fields, so which is just one line in the diagrammic language, or there can be a product of G with G square, so G to the 3, a 3 gluon vertex, or there is also a square of this commutator involved, so we have up to 4 gluon vertices included here. So that is that is different from the abelian case, and this has this wide-ranging consequences that the gluons actually build a dense foam inside the hadrons, and this foam actually makes up about 98 or 99% of the nuclear masses, so of the mass of any macroscopic objects that we deal with. In contrast to many popular science articles and so on, the Higgs mechanism is actually little relevant for the masses in everyday life. Of course, they give the mass of an electron, for instance, but if you look at any macroscopic object like this laser pointer, practically all of it is encoded in this dense foam of quarks and also of gluons and C quarks, which can emerge and disappear there and not really generated by the Higgs mechanism. And since we're dealing with strong coupling, a strong GS, this cannot really be computed by perturbation theory. If we pull quarks apart, a simple picture would be that we build more and more of this dense foam, which takes more energy. So this raises to confinement. Confinement, that's of course not an exact description, but just to continue with this picture, if we have parts at very short distance, then you say, okay, then it's not so bad anymore. We have just the exchange of a few gluons, and then the asymptotic freedom applies, and then perturbation theory can be used. Now, now let us look at what we are doing on the lattice. So what we really deal with are configurations which are a set of link variables in SU3. So we have a 4-dimensional lattice, finite lattice in some volume, and the actual configuration only consists of link variable in SU3. And the pure gauge action is given by these plaquette variables, which are also in SU3. We saw we have to multiply them over a plaquette, and the fermionic, the quark contribution, is given in the fermion determinant, which is given here. So this makes the whole statistical weight of a gauge configuration. And if we manage to generate a lot of configurations with this, with the right probability distribution given here, then we can perform such measurements of endpoint functions. Now we can look at, let's say, a pseudoscalar density, which is a gamma 5 psi. So again, this would then be some inverse of this matrix M, now with a gamma 5 included. And the gamma 5, okay, this is in Euclidean space, it does not have this factor I, so it's simply the product of the gamma 1 to gamma 4. And now what we discussed in the first lecture is that the exponential decay of such a density, of the correlation of such a density gives us the mass, and in this case this would give us the pion mass. So if we separate them and measure this decay, and so let's say at 0 that we normalize this to 1, and then we measure the decay at different distances, we can extract this coefficient here, and this is what the pion mass. And then we can take different densities here and explore different hadron masses, depending what structure we have here, and also get insight into nuclear structure, the temperature where the crossover, confinement, deconfinement, or restoration of chiral symmetry takes place, get information about the decay constants, topological susceptibility, and so on. So there is now a kind of an analog to the particle data booklet which gives the world overview of the lattice data, which is this flag report here. So these are all the data about this the latest data and accumulated from different collaborations, so on, which I will not go through in detail, just to emphasize that these results are really based on QCD. I mean, there are a lot of literature which writes QCD in the title, and then there's something completely different by using some extra parameters and so on. So we have parameters in the action, but they all lead to the same result in the continuum limit due to universality. So this is really based on the first principles of QCD. And of course, we can apply the same method to other quantum field theories. QED, it is even simpler, but it is less interesting because there we know that perturbation theory works quite well, or Higgs theory, so we will show an example of that, and many models of condensed matter and so on, so this actually defines the non-perturbative results. So for QCD, so first of all, we have this quark-gluon coupling, I called it before GS, and then we can convert it into this alpha S according to this this definition. And we know that this depends on the transfer momentum in some process under consideration. This is actually an integration constant. And if we write down the QCD Lagrangian without, let's say, with quark masses 0, let's say UD quark masses have practically 0 mass, then this is not so bad. We have basically no scale at all. The only parameter is this GS, which is dimensionless. So we would say we have full conformal invariance on the classical level, but if we quantize the system, then the conformal invariance is broken by the quantization. So this is a kind of anomaly, and this anomaly is manifest if we have now this behavior which goes like an inverse logarithm, and then necessarily we need a constant here to adjust the dimension. And if it is our phenomenological data of the measurement of this alpha S, and we can adjust this. It depends a bit on the exact definition, that's why you don't find it in the particle data booklet, but it's about this around 250 MeV, and this actually sets the scale for the hadron masses. This is the reason why all protons in the world have conducted exactly the same mass. So if it was as the classical picture, then protons could have many different masses, but due to this breaking of the scale invariance, each hadron has always the same mass. Yes?
Just to see if I'm understanding okay, this is a lattice simulation, and this is being compared with experimental data.
No, this plot actually these are experimental data, and the blue line is just a fit to this logarithmic behavior. So far this is what you find from servers or other places.
So this is a
the other plots here, that this is where the lattice starts.
This is a continuum calculation.
These are experimental measurements. Yeah, of course, experiments.
This blue line.
The blue line is an interpolation. So we have these white points here these are phenomenological measurements with some uncertainty. Don't ask me how the experimentalists can identify this alpha S somehow, and then the theory anticipates that you should have this form, and then if you perform a fit with this lambda as a free parameter, Q is the transfer momentum, then you get these blue lines. And then
lattice has nothing to do with that.
Lattice can also measure this alpha S, but not with this plot. In this plot, the lattice is not present. You can also do that, but this is not here. Yeah.
But this is the origin of this value of lambda QCD, 250 MeV.
Yeah. Phenomenologically, yes. Phenomenologically, you say you would fit it to this data and then get this value, right? If you do this fit, then you can use this as a free parameter, dimension mass, because Q has dimension mass, and then you get this. But again, it's a bit ambiguous how to do this. You can get to maybe also 220 or so if you normalize a bit differently. So it's not like H bar or C are a really fundamental constant of nature, but the magnitude fixes the magnitude of the hadron masses. And now the question is, okay, I mentioned that U and T are very light, so that means very light compared to that, 2 orders of magnitude lighter, and so that's why setting their masses to 0 does not change very much. About the proton mass would stay basically the same. And that's a hierarchy problem to ask why are 2 quarks so much lighter than other QCD. Then as I will direct most of the masses in this form of gluons. Now then the question is, okay, we never see 3 quarks or gluons, so they are confined. And now what we can do is, when we say this gluon form introduces an effective potential. What we can do is relatively easily is put static quarks at 2 different places and measure the energy that it takes to connect them and interpret this as a potential between them. And this is perturbation theory can compute this up to short distances. Then you take advantage of asymptotic freedom, which is down here. You see at higher energy, the coupling is getting weak, and then perturbation theory works. But if you are here around about 0.2 Fermi, then perturbation theory collapses, does not converge well anymore, and then this is an example. These are now lattice data. You see that asymptotically they agree very well with the perturbative calculation, but then you can still go on to much longer distances, up to about 1 Fermi, and you see here linearly raising potential, which is what we expect from confinement. Now you can say these are static quarks. This is the situation with dynamical quarks, which can also move, is actually more complicated. And still we have also in this case good numerical evidence that confinement is actually true. The picture is not as simple as here, but what we still don't have is an analytical proof of confinement. So this is there's this Clay Institute which has $1 million prizes for outstanding problems, and this is on the list. If somebody gives an analytical, mathematical, exact proof for confinement, he can get this $1 million. But so I think some people have tried, but the referees have rejected the proof as incomplete. So this, yeah, if some students think that their scholarship is insufficient, that's a good homework.
Philippe, you have this prize.
Yeah. Give me the problem. I'll try.
And now, in the last century, people performed these simulations in this, what they call quench simulation. Quench means that the fermion determinant, which is the slowest piece to compute, the most tedious numerical piece, was set to 1 when we go to a constant when we generated configurations. Of course, when you do measurements, you can then include the flavors, but this is of course a strong simplification. You can say if you have NF flavors of the same mass, you have then determinant n to the power nf. So formally we can say this corresponds to 0 flavors. Or you can say it corresponds to very heavy quarks, then the fluctuations do not contribute very much. Infinitely heavy quarks, so it's different ways to put it, but technically it means that this determinant was not taken into account in the last century, so it was simulated by putting this to 1, which brings in a systematic error, of course, but this is what people could do essentially in the 20th century, and the status was that this still gave right results up to about 10 or 15%. So this is a plot from 2002 by a Japanese collaboration. So they have 3 input quantities to fix the scale, the U and the S. quark masses, and then all the rest are measurements. So these are the violet symbols here are the numerical measurements. The black symbols are the phenomenological experimental data. You see that it matches more or less. Actually too good to be accidental, but still not the precision that we would like to have. Still usually some tension by 2-3 sigmas, in some cases more. So which was then said, well, this is probably because of this systematic mistake here. So the challenge of the 21st century is to overcome this approximation and deal with the full exact theory. And okay, this is an illustration how to measure a ion mass. So we have again this pseudoscalar density that we pull apart, and then we do this at different lattice spacings, and there are different quark masses, and we get here a linear dependence on the quark mass. Okay, so this is compatible to what is called Gell-Mann-Oaks-Wenger relation, so n pi square, so yes, linearly dependent on the quark mass, and the slope gives us this relation of low energy constants in chiral perturbation theory. So this was an example where we already got below 200 to 300 MeV quark masses. So this is about twice the value in nature. Before, in the 20th century, people had to simulate for technical reasons at very large quark masses and then extrapolate, which brings again in some uncertainties. This was called chiral extrapolation, although it's not actually really chiral, it goes to the physical point. So that's so this can be overcome now by having really even lower, actually nowadays, the physical quark ion mass, and also eliminating this quenched approximation. And this is now a celebrated result published in Nature by a collaboration known as BMW. So they simulated, let's say, they measured, say, the ion mass at different distances. So you have this correlator, and you take the correlator at a shifted value +1, and the logarithm of that gives us the mass. And you can do this at different time separations, and then in the beginning you have a contamination by higher excitation. So this is typical that it is at very short distances you have a contamination. So you have to separate it well enough that only the first energy gap contributes, and this is what gives the mass. Now if you separate it too much, then it's bad again, because you have this exponential decay, and then it's very difficult to measure this and distinguish it from zero within the statistical noise. So you have to look for an intermediate window, in this case between 8 and 12 lattice spacings, where you find a plateau, and these plateau values, depending on the densities that we correlate, can then be identified with different hadron masses. Now, so once this is done, you say, okay, you do this at different, you repeat this by varying let's say, the light quark masses, and then you have each time a different ion mass, and we can then extrapolate to the physical ion mass. So this is 135 or 140 MeV, so this is an input. This we do not measure, this is an input, and then we extrapolate the data for the nuclear mass from these points here down to this physical value of the ion mass, and this is then the result for the nuclear mass. And okay, in this case, n pi was already close to the physical value. Nowadays it's really there. So here they still have to extrapolate a little bit. Nowadays this extrapolation is not needed anymore. And they looked at lattice sizes which were about 4 times larger than the inverse ion masses, the correlation length here, which we said sets the scale for everything. So since finite size effects are exponentially suppressed, this is actually safe. So these finite size effects will make a small, will not do much harm in this case. So this is a size of about 4 Fermi in this case. This is about an inverse Fermi. And what is more worrisome are the lattice spacing artifacts. So they simulated this at 3 different lattice spacings, which are shown here by the different colors. And we see that the extrapolation seems quite safe down here, and there are sophisticated extrapolation techniques to get this final value here. And now if they do this extrapolation, they get, for instance, for the nucleon mass this value. This is statistical and systematical error. If you take it together, that makes an uncertainty of about 3%, and it is nicely compatible with the value in nature. And then you can look also at different heteromasses. Again, we have this psi here. This is used to set the scale. So this is measured, and then taking the phenological value, this is converted to set the scale in MEV, because we only have lattice units to start with. And then we adjust the UD quark masses. They are assumed to be the same here to get the pion mass right. And then we have the S quark mass, which is adjusted to get the kaon mass right. So these three terms are input, but then all the rest is measured and compared here with the phenological results. And okay, this is the width of the measurements, but the bar here is the phenological value of rho k, etc. And we see they all agree now between the errors, and the errors are small, a couple of percent. And until, okay, there are different collaborations which have similar results, but until a few years ago, nobody could say if UCD from first principles would really reproduce the hadron spectrum. Now we see that this agreement is fully convincing, that you let some quarks interact and they give you the exact hadron spectrum. Now a little bit of propaganda for our collaboration, mostly with people in Germany and the United Kingdom, actually mostly in Scotland, and then some outside persons in Japan, Russia, and now Mexico. This is what we got. We have to get the scale, we have used f pi, the pion decay constant, so we only need here two inputs, the pion and the kaon mass, and all the rest are the red symbols here are the lattice measurements with their uncertainty already summed over statistical and systematic, and we see that everything follows. These are the names of the hadrons. Everything follows exactly the values in nature. The black lines are the values in nature. To explain a little bit how our approach works, traditionally what I showed before is that people first try to get the kaon mass right, and then try to push for light pions as far as they got. And now the different strategy that we applied here is to start from an SU3 flavor symmetric point. So where UDS quark have the same mass, and then the pion and the kaon would also have the same mass, and then start from there and drive the light and the strange quarks masses apart, such that this sum here remains constant, and then we have a kind of a guided chiral perturbation theory guided extrapolation, where the leading order and the corrections here cancel, so we have a bit a safer way to extrapolate. And so okay, we are on this line. Then phenology, which first we have SU3 flavor symmetry corresponds to this blue line. Then the physical mass summed here gives us this, and then we drive them apart, making the S heavier and the UD lighter, and we extrapolate to this point. So this is a kind of a safer extrapolation. So this is where we have an advantage, a technical advantage, and then we can we get this kind of fan plot. So this is again the SU3 flavor symmetric point, and then we can extrapolate here to the different hadron masses. Here we make the UD lighter and the S heavier, and extrapolate here to the limit. And okay, this is then this was for the mesons, and this is for the baryons, septet and decuplet. So this is hard to read, but here the colors are the same as above. So we see that the heavier it gets, the more difficult. So here everything works beautifully, but the heavier it gets. So here we have this red symbols here are the phenological value, the experimental values. Here we see that if we deal with heavy objects like this omega, then we still have some uncertainties to deal with, and that's why the errors are a bit larger up here. But still, this is the plot that we had before, and we see that the hadron spectrum comes out convincingly to a modest inaccuracy. And okay, this is now done on a set of supercomputers in different countries. Not going into details about that. Just to summarize a little bit the status. So in Wilson, we remember in the 70s and early 80s he worked out the concept of lattice QCD, and he started first experiments, and in the late 80s he suddenly changed his mind completely, and I think it was before he quit the field, the last Lattice conference where he attended in '89, not before my time, but people told me that he suddenly gave a very pessimistic talk and said, oh, this method doesn't work at all. You would need at least 256 to the 3 times 512 points with dynamical quarks and so on, and then he estimated how much computing time increases each year and came to the conclusion that within 30 years you will not get to any result which is phenomenologically relevant. So it's basically told people you should go home, this doesn't make sense. And he did this himself. He left the field and started to work on light quantization, I think not very successfully, but most other people ignored him and continued to work on the field, and that in the last century his quenched results and now the dynamical ones. He was not completely wrong. It took time to get really useful results, but less than 30 years, only about 20 years, and now we can confirm, let's say, the hadron spectrum, the light hadron spectrum, up to an uncertainty of about 3%. Now, coming next is, of course, we can just push this ahead, then we get to percent or sub-percent level, but this is not exactly the same as before. At some point we have, for instance, and people are doing that now, to include QED effects. Of course, quarks also have an electric charge, which has been ignored so far because it makes a minor correction, but if we want to get to a sub-percent level, then we have to include that, and also, for instance, the effect that U and T quark masses are not the same. This is usually not done before, but also this has to be, so we need to include new elements here. And an outstanding challenge is, of course, certainly are the excited states. So that, for instance, the Roper resonance, which is a resonance of the nucleon. This so far is known phenomenologically, but so far nobody manages to calculate it. The lattice results are not compatible with their phenomenological values so far, but they have large uncertainties, and there is no other method known for that. So there are outstanding challenges. Because if you measure the hadron masses by an exponential decay, so here you have this exponential decay, then you find, okay, I need to the minus mx, okay, but now if you want the excited state, you will need a subleading contribution, so you subtract that, and from this deviation here, you should then extract the subleading, the higher mass, and this is obviously much more difficult and much more sensitive to mistakes, so that's a heavy challenge to still work on. But generally speaking, so far we have managed to do post-stitches, so reproduce known results and show that they are based, they can be reproduced from QCD. Challenge for the future is also to proceed to real predictions, and at least we have one nice example for that in 2005. This is a US lattice collaboration here, predicted this heavy meson with a mass of given here, and 1 year later it was found quite exactly there. So this was celebrated as a great success. And then a little later there was something called the FDS puzzle. This is a decay constant, which the lattice gave a much lower value than the Bell experiment. And then a little later, okay, the value of the lattice moved up and the Bell value moves down, and so they met more or less in the middle, and now it's not considered a puzzle anymore. So this, at least it gave the right trend, so we can count this maybe as half a prediction, right? Half a right prediction. And everything seems to proceed smoothly so far, and this is actually not typical for the history of science, that all this, following Wilson's concept, of course it's not only increased computer power, it's also increased better algorithms, better formulations of the lattice gauge action and so on, a lot of difficult different tricks involved, that's why it was faster than Wilson's estimate. But then Lüscher, who has the role of a kind of a group of the lattice community, at least in Europe, he attracted first attention to the following problem. Now, so far, the simulations were usually done between lattice spacings between 0.05 and 0.1 Fermi, and then you can extrapolate. This is what we have seen in this E and W collaboration. I think it was in this range, right? Here a bit higher, but this is usually where people extrapolate. Now, of course, since this is the worst source of systematic errors, people, of course, want to make the lattice even finer, lattice spacing even smaller. So it takes more computing time, but maybe we can afford that. But it's not only a question of computing time, because we know QCD is a theory which has topological sectors. And once the theory is very continuum-like, then the gauge configuration cannot be deformed from one topological sector to the other anymore. That's if in the continuum this is impossible, that is the definition of topology. And the algorithm actually generates this Markov chain, so one configuration after the other, based on the previous configuration with smaller changes. So if we are getting close to the continuum and we perform such local updates, we will have the problem that we get stuck in one topological sector for a very long time. So roughly speaking, the picture is a bit like that. So let's say we have here different topological sectors. So here this would maybe be trivial solution, one instantone and two instantones, and then you can fluctuate around, and we should probe. So this is the space of configurations, parameter of which has actually infinitely many parameters. But I say this is one parameter, and this is now the Euclidean action. So we should actually probe all the possible configurations with the right statistical balance, statistical weight to get the right result. And now our simulation is likely to be locked in one, fluctuate around in one such sector. If we go closer to the continuum limit, these barriers get higher and higher, and we don't get out here anymore. So we are stuck here for a very long time, and even the history of measurements looks maybe fine. We seem to get a small statistical error, but we can get a completely wrong result because we missed the other contributions here. So that, if we take the lattice spacing even smaller, this could be turned into a serious problem. So this, what Lüscher proposes is the use of open boundary conditions. Then the topological charge is not integer anymore and can change continuously. This can overcome the problem in some sense, but it's a pity to give up the integer topological values, because topological charges, because there are predictions, for instance, in small volumes called epsilon regime in each sector, which can then be compared to lattice measurements, so that all this would be lost. So what we are working on is an approximation. If we have only topologically limited measurements at hand in different sectors, so this would be Q0, 1, 2,